with the record. Okay, we are working on the third part to chapter 9. Remember, after chapter 9, we have chapter 10, and that will pretty much be the end of this class. And can you imagine the semester is almost over? To me, it feels like it just kind of rushed through, and at no point during this time did I feel the semester was slow. Everything has seemed to be very fast. Anyway, to wrap up this chapter, we're looking at the energy exchange at standard conditions. So let me get the right color pencil or pen. Okay, so what we just did here was calculate delta H of the reaction by looking at the bonds broken and the bonds formed. And essentially, when you're looking at this, bonds broken, when bonds are broken, energy is released. So the energy release here tends to be positive. When bonds are formed, energy is required. And so in this case, the energy is going to be, well, actually, I'm saying it the opposite way. When bonds are broken, they release energy. Right. Okay. And so when bonds are formed in this case here, the direction of energy change is usually negative in this case. So you see right here in the equation, what we're trying to see is the end from the beginning. So we're seeing right here, bonds broken minus bonds formed. And when you have these values provided to you in a question, you take your bonds broken, add all of those up. For you to see the bonds that are broken, you actually have to look at the lowest structure. So back here, I explained how you have to take the formula given to you, draw the lowest structure out of it so you can compare the before and the after. So in the before, you can see what the chemical reaction was, what the connectivity was. In the after, you see the new bonds that were never there before that have now been formed. Okay, so when you have the bonds broken, add all of those up. These energies will usually be positive. Bonds formed, the energy is negative. So for that, when you add these two, as they say, you're essentially taking the total bonds broken energy and then subtracting the bond formed from it. And that will give you the delta H of the reaction. So remember, we've been figuring out delta H's for different scenarios. And delta H is that energy, the enthalpy of the reaction, the energy contained within the reaction. Okay, so this is what we looked at. Now, as I'm working on this class right now, I just finished dealing with enthalpy for my next class, my 1412 class. And so there's a lot of similarities. Just be aware there's so many different kinds of energy in a chemical reaction. There's some energies that are being transferred, some energies that are due to randomness, energy due to internal energy. So you want to make sure you're aware of which energy you're dealing with. Okay. So in this case, once again, we're dealing with the enthalpy, which is the energy of the reaction. Now we're moving on to the enthalpy, a different kind of enthalpy, the enthalpy of formation. So this is the energy released or energy exchange in forming compounds. Okay. So as we continue to look at chemicals from the point of view of thermodynamics, the people in thermodynamics tend to look at transformation in terms of energy. It would be like a financial person looking at things from the point of view of money. Anytime you talk to them, they're always thinking, well, how much does it cost? What is the cost? Is there a return on investment? Everything for financial people is always money, 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 money. With this group of chemists, everything is about energy. So we're now looking at the energy that is required. It could be positive or negative in forming a compound. So for us to look at that holistically and to look at that in a standard way so everybody can agree on the amount, we will look at the standard state. So we have to define what exactly is the standard state. These are a specific set of conditions in which the experiment is performed. So we're told it is the state of a material at a defined set of conditions. So it makes more sense to think about the lab, right? Chemists like cohesiveness in their results. They want to make sure if you are in America performing an experiment and someone is in London or in Germany or whatever performing the same experiment, that you get the same results, right? that kind of, there's accountability there, legitimacy, and things like that. So to make sure everybody has the same results for the same experiment, have standard states. So for standard states, if you're working with a pure gas, you want to make sure the gas is at exactly 1 atmospheric pressure. If the compound or the product you're dealing with is a gas, it has to be at 1 atmosphere pressure. If you're dealing with a pure solid or liquid, make sure it is in its most stable state form at exactly also 1 atmosphere pressure. And then the temperature usually is kept at 25 degrees Celsius. So now we're being told when someone says the term standard conditions in chemistry, that means pressure is 1 atmosphere, right? That has been stated. Temperature is 25 degrees Celsius. Okay, what if you're dealing with a solution though? What if it's not a pure solid, pure liquid, or pure gas? What if it's a solution? They provide a standard condition for that too. For your solution, your standard concentration has to be 1 molar. Okay? So now that we know all these conditions, we now can perform what our target was, which is to figure out how much energy does it require to make a compound. What is the energy required to form a compound? Okay? So we're told here the standard enthalpy change, delta H, is the enthalpy change, which is the energy exchange when all reactants and products are in their standard states. So we're saying here that when we're trying to make 1 mole of a compound, a pure compound, we want to make sure we're using ingredients that are in their standard states because it helps for us to do this experiment in the standard state. That way, people trying to repeat our experiment to get the same number, they can follow suit and they can get the chemicals in the same state. Relating this to life outside of chemistry, it would be like you making a meal, right? And somebody said, "Oh my goodness, I love this meal. It is so tasty. The ingredients taste different. What do you do?" And you said, "Oh, I used organic ingredients." If the person wants to get the same outcome you got, they have to use specific ingredients. In this case, your ingredients were organic, right? So our ingredients here, our reactants, are reactants in the standard state. So if you use reactants in different state, you will not get the same value of delta H. Now that we have our reactants set up, we're going to define what we're going to be calculating. Standard enthalpy of formation, delta HF. This is the enthalpy change, once again, the change in energy for the formation of 1 mole of a pure compound from its constituent elements. The product we're making is 1 mole of a compound. Not just any compound, it's got to be a pure compound because the reactants are pure, right? They're pure and they're from their standard states. Okay, once we use pure reactants from their standard states, we're going to be making this amount is specific. It has to be 1 mole of pure compound. Okay, and so we're told the elements must be in their standard states. Of course, they're going to be pure. And so we set it up that way, not because we're trying to taste it and we want it to taste good. We're trying to make our math easy, okay? So this is where you see scientists. Like I said, tell you have to read between the lines. The chemists want to make their math easy. Why do we care if the reactants are in their standard state? Because of the statement here. The delta H of formation for a pure element, which is our ingredient to make the compound, right? Remember, elements are used, elements add up, or react, of course, add up or react to form compounds. So we're using the elements as our reactants to form compounds, right? So our ingredients, our elements, if they're in their pure form in the standard state, then the energy required to form them is 0 kilojoules per mole. So it's kind of like saying these ingredients don't really require energy. They have no calories, no energy. But when they come together to form compounds, that process of them coming together, that requires energy, right? But the ingredients by themselves, there's no energy required to form them. That's what it says here. The delta H for the formation, which is delta H is the heat of formation for the pure element, only if it's in standard state, is 0 kilojoules per mole. Okay, I think I've over-explained that. Now let's look at this table here. This table here is the table showing you the standard enthalpies of or heats of formation, right? So in other words, if you are trying to make a compound, say you work for a company and trying to make a compound, and they're asking you, well, how much is that going to cost in energy? If you're employed as a scientist, you want to know how to figure this out. Depends on what compound you're trying to make. If you're trying to make glucose, let me look at glucose right here. Let me make this a little bigger, right? It will cost you 1,273.3 kilojoules per mole of energy to make glucose. Okay, different amount of energy to make sucrose. So it costs different amount of energies to make different compounds. Well, let's look at the ones that have zero in here. Bromine has zero. It's bromine in liquid state. This is the standard. So I put STD for standard. Okay, this is the standard state of bromine, the natural state you find bromine in when you encounter it in real life. Calcium, this is the standard state of calcium in real life. Okay, so look over here. For all the elements that have 0 kilojoules per mole heat of formation, these are the elements in their standard state, in their pure standard state. So we see 0 there. Let's look at one that's not in the standard state. Okay, apparently carbon in the graphite form is 0, right? That's considered standard. But the same carbon in a diamond form is considered to have an enthalpy. So this is not considered to be standard. So you cannot use diamond in the place of graphite. Okay. So it's important when you're looking at this table to pick the right quantities. Chlorine standard form 0. Chlorine non-standard form has the value. Okay. So remember, you want to pick the ingredients, the reactants in the standard form, which have a delta H value of 0. So only the ones that have 0, 0, 0, 0, not the ones that have numbers. Those are your valid ingredients. So now let's go ahead and set it up. Based on our understanding of that, now can we work this out? So I'm going to be adding pages because I'm trying to not use the ones I already had, right? Okay. So in this question here, and I do prefer the yellow, it's a lot brighter. In this question here, we're told, write, oops, wrong color, write equations for the formation of magnesium carbonate. Okay, context here is standard enthalpy of formation, and we're trying to make magnesium carbonate. So for magnesium carbonate, let's see. Oh yeah, we're trying to make the compound magnesium carbonate that's a solid. We need our ingredients, the elements, and they have to be in standard form. So what I'm going to do here is, oh, they kind of wrote it for us here. That's okay. I'm going to work it over. I'm going to work it out over again. We're trying to make magnesium. Remember, the definition of standard heat of formation is the requirement we have to make 1 mole. So the coefficient here has to be 1. It cannot be anything else, okay? So I'm going to erase the 1 later on, but I'll leave it here for right now to remind us we're only making 1 amount. Okay, we're going to make it from the elements. So the elements here are magnesium, carbon, and oxygen. They have to be in the standard form. So I have to write oxygen as O2 because in the standard form, oxygen is O2. So to kind of help me out a little bit, I go back here and see what magnesium. Do we even have a magnesium here? Let's see. I work on a computer a lot. Let me find my glasses. Working on this computer a lot. By semester end, my eyes are all messed up. I have astigmatism, so it's like the screen's so close to me right now, it's sort of blurry. Okay, that's a little better. Hold on, magnesium. They don't have magnesium here, but I can extrapolate from, let me pick another metal. Do they have any metal here? Yeah, from sodium. Sodium in its natural state is 0, so magnesium in its natural state will also be 0, okay? So I can confidently say magnesium will be a solid because it's a metal, okay? I know carbon has to also be a solid. I saw it back here. Carbon, yeah, solid and graphite. That will be 0. So I'm going to put here solid. I'll just write down here graphite because it has to be that for us to get it in 0. And then oxygen, that's how they wrote it here. Oxygen gas. Here, where is oxygen? Oxygen, gas, that will be 0. Okay, We're trying to make it. Now, this is the flaw of the design. People who made this in the PowerPoints, we don't have magnesium carbonate in here. If you look over it, it's kind of alphabetical, sort of, not really, but yeah, it's organized. There is no magnesium carbonate here. So I have to rely on this number they provided us in the solution, right? But imagine magnesium carbonate was part of the table. In your homework, and if this question is on the exam, they will provide you with those numbers, okay? So, oh, I don't have this number right here. Let's see. Oh, there it is. Right. They will give you this number. It says 10, let me write this down. 1095.8 kilojoules per mole. Yeah, and it's negative. Okay. So right here, negative 1095.8 kilojoules per mole. Now I have to balance this out, right? The chemical equation has to be balanced. So let me see. It shows that I have 3 oxygens, so right here 3/2. In this case, to balance it out, you can use fractions because the goal is you have to make 1 mole, right? Number of carbons is 1, this is 1. Now I can erase this part here. I don't need the 1 there. Okay, remember each of these reactions are 0, 0, 0. So essentially we're saying the change, delta H of formation, okay, so delta H of formation is, let's see, products energy minus reactant energy. This is something that we saw before. So our product energy here is this number. So that will be negative 1095.8 kilojoules per mole minus the reactants. Look at all our reactants. They're all 0 kilojoules per mole. So 0 kilojoules per mole. So when you subtract these two, we get the delta H of formation of, I should have written here, magnesium carbonate. Sorry, I got distracted from the text. That will be negative 1095.8 kilojoules per mole. So all we're saying here, even though the ingredients did not require any energy in their formation, when you are making magnesium carbonate, this is the amount of energy that gets released. Okay, it costs energy to make magnesium carbonate, or energy is exchanged in making magnesium carbonate, and this is the amount of energy that gets exchanged. Okay, even though the ingredients did not have any energy. And so this will be essentially, we'll say negative 1095.8 kilojoules per mole is the enthalpy of formation for magnesium carbonate. Okay? So we've pretty much answered that question. We're going to do the same thing, but this time we're working it out for glucose. Okay, I saw glucose over here because I think I highlighted it. So this should be a lot easier because we have the numbers here, right? So let me see. Oh, let me move a little slower. I keep forgetting that the way I move the screen affects your experience. We're trying to make glucose this time, right? So we're trying to work on enthalpy of formation. So you want to know how to write the equation enthalpy of formation. And this time what we are forming is glucose, so C6H12O6. Okay. Remember, you want to write your product, C6H12O6. And then you have to find its physical state. So the physical state here of glucose, I want to say when glucose is formed, it's a solid. So I'm going to go back here, C6H12O6. C6H12O6. I see it here. It's a solid. And I'm going to write the number down, negative 1273.3. So making all of these compounds actually is causing the system to lose energy, to release energy. Okay. So I'm going to scroll down slower and write down here. Okay. From the table, I got the delta H of this here to be negative 1273.3. 0.73 kilojoules per mole, which is okay. We're making 1 mole, right? This is going to be a solid. So we have to find the ingredients that make this glucose. What are the elements? They have to be in the standard state. So I know I have carbon, right? I know I have hydrogen, but remember hydrogen is part of that Brinkerhoff family. Brinkerhoff. So for any of these Brinkerhoff elements, you have to write it as the element sub 2, right? So hydrogen, and then we have oxygen, also part of that Brinkerhoff family, so it's going to be sub 2, okay? Carbon should be the solid, and this should be graphite, just like we saw in the one above here, right? Hydrogen, this should be a gas. I'll confirm it after I'm done writing. Oxygen should also be a gas, right? We want to set it out so that remember these are 0 kilojoules per mole, 0 kilojoules per mole, and then 0 kilojoules per mole. We want that deliberately. Okay, when I balance this out, let's see, it shows 6 carbons on the right, so this should be 6. It shows 12 hydrogens, so I put 6 here, so 6 times 2 makes 12. It shows 6 oxygens, right? So I should put 3 here, correct? Yeah, my goal is to balance this equation out. Yeah, 6 carbons. So let me double check to make sure that this is in the correct form. Then I'll figure out the enthalpy of formation of the whole compound, right? From the ingredients that are in standard state. Okay, let me go back here, check real quick. I'm just showing you how to use the table once again. Okay, let's see. I'm looking at carbon. Carbon in the standard state, the graphite is 0. Yep, use that one. What is next? Hydrogen standard state, H2, 0. Next, oxygen standard state, O2, 0. Okay, I used the right ingredients, right? Okay, now that I've done that, I have to figure out what the overall transformation is. The overall transformation, delta H of formation, when we're trying to form the compound, right? In the standard state, oh, I forgot to write standard state here. Standard state. It's just saying the ingredients are standard, and the compound here is C6H12O6. Once again, we take the product energy that we got from the table minus the reactants. Now, if you have more than one product, you're going to add them all up. If you have more than one reactant, you're going to sum them, right? Add them all up. So add this to get 0 kilojoules per mole total, right? That's okay. This is our reactant. This is our product. So our product here is negative 1273.3 kilojoules per mole, and our reactant is going to be 0 kilojoules per mole. So ultimately, we're saying in order to make glucose, 1273.3 kilojoules is for every mole that's made, okay? And so we got this. Once again, the objective here is to be able to calculate the enthalpy of formation. The other objective is to be able to write the formation equation here, okay? So let's see. They did this. Oh, I kind of wrote it in here, trying to be lazy. Yeah, so you see how they work theirs, right? So here's the enthalpy of formation right there, enthalpy of formation. Oh, I guess I wrote mine in here, but you can see right there. Now they have to balance this bottom one out. Oh, finally, I see. They balance it right here. And the enthalpy of formation, right, just like I showed you. Okay, so let's go ahead and move on. So now that we see this, we're now that we know how to figure out the enthalpy of formation, they're telling you, okay, because remember with chemistry, we're always building up. Learning, it's like we're learning to add, to subtract. We're learning to add, then we're learning to subtract, then we're learning to multiply, and we're learning to divide. And then we kind of put all those things together and do a problem where it combines all those individual aspects that we learned, right? To do something bigger, to accomplish a bigger task. And then you have to use PIMDAS then. Anyway, over here, we're now saying once you learned how to figure out the delta H of formation, we're now going to calculate standard enthalpy change for a reaction, but this time you're going to be given delta H of formation, standard form of reactants and product. So you are not figuring out delta H of formation. They figured it out for you, but they want you to use these to figure out standard enthalpy change of the reaction. To kind of give you a shorthand form of this in symbolic terms, you are calculating, so we're calculating delta H of reaction from delta H of formation of reactants and product. That's the bottom line. Earlier, you were figuring out delta H of formation of the product, right? The compound. Now they're giving that to you, so you're not looking for that. Well, it depends. I've seen questions where they give you delta H of the reaction, they ask you to solve for something else, but we're not going with that. Let's stick with where we are right now. Right now, this is our goal. We're calculating delta H of the reaction from delta H of formation of the reactants and the products. I keep forgetting this one right here. Okay, so that's what they're telling you here. So they're telling you our plan is, if you were given delta H, now they have all these symbols here. These symbols, you know, in chemistry, all these symbols, they do have importance. So with this part here, you will be given a balanced equation. So they're not telling you right now, but you, at some point, you will have a balanced equation. And we know in the balanced equation, we have those coefficients, right? Those numbers, those multiplier, we use those to balance, right? So I'll call them the coefficients, right? And we're using those to balance the equation, essentially. So since the coefficients multiply the number of chemicals required, you're going to be using those here. So the coefficients, so N and M, N and M are the coefficients. Oh, I see they use N each time. Okay, I'll just stick with that. N is the coefficient. Okay, so you can see here it tells you we start off with the product first. So take all the products you have and add their delta HF to each other. That's what the symbol is saying. This symbol says sum. Add them up together. But if they do have coefficients, multiply the coefficients by each product before you add them up together. That's what this is saying. And it will be simpler when I show you how it works out or how it plays out. And then subtract from the product, subtract the reactants. Same thing with the reactants. Take the coefficients if they're present, multiply by delta HF of each reactant, add standard state, don't forget that, and then add those all up together. When you're done, you will have the sum of the products, delta HF, as standard state, right? Multiplied by the coefficient minus the sum of the reactants, delta HF, at standard state, multiplied by the coefficient. Anyway, you're essentially taking products minus reactants. Okay, all your products minus all your reactants. Okay, let's work this out. Now, in this problem here, let's see. Because this is actually an example. I'm trying to see. This is an example. They gave you the heat of formation of each of these. So I'm going to write this. I'm trying to see. Yeah, I wrote on this before. I'm trying to see how I can change this right here. They gave you the enthalpy of formation. Oh, okay. I'm just going to use this right here. So what they're doing here in this question, based on what I have written here, they're showing you that if you're trying to find the delta H of formation, you can either use Hess's law or you can use the equation we just learned. We learned Hess's law before, so I'm going to follow what I wrote here before. I'm going to skip over using Hess's law, and I'm going to just show you how to use the equation, okay? So we're going to use the equation. And like I just said, we're going to add up all the reactants, add up all the products, take the product minus reactant, and that will help us find out delta H of the reaction. So we're doing this Finding this, remember, this is the sum of all the products, delta H, minus the sum of all the reactants, delta H, of formation. And I'm keeping the equation very simple right now. You know the details, right? Now I need to find the delta H's. They're right here. Delta H of formation of the formula CH4. So delta H of formation at standard state here is negative 74.6 kilojoules per mole. I'm going to write it right here. I wasn't given one for oxygen. Let's see. Delta HF at standard state equal negative 393.5 kilojoules per mole. Then over here I have the same number, delta HF. Do I have room? Really, do I have room? Which is equal to negative 241.8 kilojoules per mole. That's water, right? Okay. Did they skip over oxygen on purpose? Oh no, they didn't. Remember, delta HF of the elemental oxygen in a standard state is 0. So there's no point in giving that to you. Okay? So if you're working on a problem like this and you feel like they have forgotten something, ask yourself, is there a possibility from a table somewhere that this is 0? Is there a possibility? Okay. So remember, our objective is to find delta H. So what I'm going to do here is I'm going to work on finding the sum of products first. Okay. So is this balanced here? Let me make sure. C, C. Let me move these right here. These are from what I wrote before. Okay, C, C, H4, H4, O4, O4. Okay, I'm going to start with the product first. So I'm starting with this side here. Okay, my products are CO2 plus 2H2O. This. So I'm adding up my products first. That's my goal for right now. Okay. For my product, I need just the carbon by itself. How many moles of carbon do I have? I only have 1 mole, so I'm going to write here 1 mole, right, for carbon times this number right here, negative 393.5 kilojoules per mole, right? Because you see the coefficient here is 1. And then I'm adding that, so I'm going to put this in parentheses. Remember, this is for CO2. I'm adding that to, my coefficient here is 2. 2 moles times, what's my number here? Negative 214, negative 2, sorry, for 1.8 kilojoules. I'm running out of space per mole. Okay. This is stuff I wrote before. Okay. And remember, this part here is for my water, my 2 waters, right? Okay, the mole and the mole cancel out. Oh, I didn't write this. I forget my rules. I forget my own rules that I put in place. Kilojoules per mole. I like to write that as a fraction just so you can see how it cancels out. So my unit here will be kilojoules, and then this one here will be kilojoules because the moles cancel out, right? Oh, this number will be the same. It will still be negative 393.5 kilojoules. And then this one here for right now, I'll write it as plus. And I'm looking at this, and this might be negative, right? Let's see. 2 times 241.8. Negative 483.6. Yeah, I multiply these two out. So when you have adding and subtracting like that in the parentheses, these essentially work out to, let me see, let me open the parentheses here. So I'll end up with negative 393.5 kilojoules. And then these end up being minus, right? A positive multiplied by negative is negative, so 483.6 kilojoules. And so we end up with negative 393.5 minus our 483.6. Let me see what we get here. Okay, so my answer came out slightly different. It came out as negative 877.1 kilojoules. Okay, let me see what they have. Oh, I guess I erased that. So, oh, I guess it's correct. So this is our product, right? Okay, I was judging it too soon. Now we're gonna work on the reactant for the reactant part. Okay, for the reactant part, I'm now essentially working on, let's see, this part right here. I'm working on CH4 and then 2 oxygens. Okay, so for our sum of reactants, I have CH4 plus oxygen. So the CH4, how many do we have? Just one, and then we got 2 oxygens, right? So I'm working on this part. So CH4, let's see, what is CH4? I need to write this down. CH4 is negative 74.6 kilojoules per mole. Oh, that's all I need. Okay. So CH4 here is 1 mole times 74.6 kilojoules per mole. And we know that oxygen, we essentially have 2 moles times 0 kilojoules per mole. So this whole thing will be 0, correct? I forgot to put my negative here. This is supposed to be negative. So we end up with negative 74.6 kilojoules per mole. Okay, so now I'm going to do what they have here to get the answer that they have. Well, when I say they, I mean this is me before. Okay, so remember, delta H of the reaction is going to equal, let's see, sum of products minus sum of reactants. So I try to keep the formula simple. We've already done all the math. So what did I have before? Negative 877.1 kilojoules. Oh, sorry, the moles cancel here. Man, I'm forgetting those things. This is what I get for staying up too late. Staying up late affects your mind, man. It really affects your mind. Okay, so right here. So I have that right there. And then I am subtracting. So this is minus, right? Subtracting minus 74.6 kilojoules. Okay. So what do we have here? Okay. So this will become negative 877.1 kilojoules plus 74.6 kilojoules. And we end up with negative 802.5 kilojoules. This is delta H of the reaction at standard state. Okay. So once again, I broke it down to products. I did the products part, I did the reactant part, and then recombined them and then worked it out. You don't have to do it that way. You can combine them together in one page. When I'm teaching, I try to be more methodical because I'm teaching. I'm doing it for it to make sense for somebody else versus just making sense for me. Okay. When I'm writing for myself, I usually take a little bit more shortcuts, a little bit more leeway. When I'm writing for others, I try to be more careful. So there. Okay. So let's see. So they work it out here. They use Hess's law, and I'm not going to go over Hess's law again because that was covered before. And they use Hess's law to get the same product. And then they use this process here, using the enthalpy to get the same. When I say product, same answer, right? Okay, so here's another question. Once again, in this here, our goal is to go over standard enthalpy of formation. Okay, so we're using standard enthalpy of formation to determine delta H of the reaction for the following reaction. Oh, okay, look at that. I already have the standard enthalpy of formations written on the top. So why would I go ahead and do anything else? So here, I guess I went back to the table and got these numbers. So you need to have these numbers because you need delta H of formation, right? To get the delta H of reaction. So let me try to erase that without erasing the individual values. So we have the delta H of formation as standard state for each of these, right? You see that here? I am going to copy this over. Oh, I even wrote it down here. Guys, let me do this. And I broke it down again. Okay, now I'm gonna work over everything. Don't worry. I'm gonna do it step by step. Because I don't know what I did with this recording. Apparently they're erasing my recording, so I need to go back. I need to do something to save my recordings. I mean, they're not the best professional with all these graphics and stuff, but they're my hard work. It's my life. Not really like my life, you know what I mean? And Blackboard is erasing it. Okay, so let's see. Oh, we're trying to figure out delta H of the reaction. Just like before, we'll take the product, the sum of delta H of formation of the products, get all the products together, then figure out all the reactants, add them all together. Okay, just like we did before, I will start with the sum of the enthalpy change. Okay, so somehow if I'm going to write this, I may as well write the change, right? Because that's part of it. Change of the enthalpy of formation and standard state of the product. I'm going to add all of these up. Remember, I'm including coefficients, right? So my products here are 4NO. I'm rewriting it because the equation is currently cluttered. And then the 6 hydrogens, and then 6 waters. Each of the water is negative 241.8. Hey, we just saw this number, kilojoules per mole, and we're seeing it again. NO is 91.3 kilojoules per mole. Okay, I'm going to be dealing with this right now. Okay, so we're going to be working with, I just say equal, 4 of these. So 4 moles times, and this is positive, right? 91.3 kilojoules per mole. And this is for the 4 NOs plus 6 moles times negative 241.8 kilojoules per mole. And this is for the 6 waters. Okay? So the moles and the moles cancel out, the moles and the moles cancel out. Our answer will have the units kilojoules, and this will be kilojoules also. And we have a positive here and a negative here, so that will end up being negative. I'm kind of skipping steps now, right? Because I already showed you that before. Okay, so 4 times 91.3 gives me what? 365.2. Here I have 6 times negative 241.8. 6 times negative 241.8. Okay, so I got the negative already here. I can't forget that. And then this becomes 41450.8, right? Okay, so when I combine these, what do I get? I combine these, and let's see. I have the second number plus 365.2. Okay. Negative 1085.6. Trying to see why my number is slightly different. It's 91.3. So let me do this real quick. 4 times 91.3. 365.2. Okay. And then 6 times 241.8. I'm trying to make sure I copy this right. Okay, then I take my number. And then I add 365.2. Yep, that's what I get. Okay, this is what I get for the first half reaction, the product side. Let me work on the reactant side. Delta H, F standard. This time is the reactants. On the reactant side, what do I have? This time I'm dealing with what? NH3. So I got 4 NH3 plus oxygen. And how many oxygen did we have? 5. And the 4NH3 is negative 45.9. Negative 45.9. Okay. So I'm going to erase this bottom part here. and then work it out. Okay, so for my equation, I need to write a little slower. I'm running out of space. Okay, so as I work this out, I'm going to have, since it's 4 here, 4 moles times negative 45.9 kilojoules per mole. You know this one's going to end up being 0 kilojoules per mole, whatever, it's 0, right? Negative 45.9. So let me make sure I'm doing this correctly. 4 times negative 45.9 and 183. Okay, let's do this. 183.6 kilojoules, right? Because it's kilojoules. Okay, wait, I'm gonna write it here. I know I don't have a lot of space. I'm opening up a whole new page for this, y'all. Okay, delta H of the reaction is gonna be, this is the product, right? So negative 1085.6 kilojoules minus the reactants, negative 183.6 kilojoules. And so we end up with, let's see, negative 1085.6. Oh, this becomes plus, right? Plus 183.6. Okay, we end up with negative 902 kilojoules. Okay, let's see what they got. They worked it out here. Products minus reactant, they had their little tables. Everything looks good. Oh, look at that, negative 902 kilojoules. Now they work it out in one go. They can do that. They can afford that luxury. They have everything on the same page, right? Okay. So as we look at this right here, we're seeing that, oh, we're doing good. We're doing good with time. So we're working on standard enthalpies of formation. So what we see here is the enthalpy of formation is showing you standard enthalpy of formation practice. Oh, I forgot. We don't usually work on practice problem, but what I'm going to tell you here is recognize the type of reactions, right? So here, as we're working on this problem here, remember that we have learned this so far. So here I saw myself summarizing. If you're looking at chapter 9, part 1, chapter 9, part 2, and then now chapter 9, part 3, we have figured out delta H's of reaction using so many different methods. Delta H's of reaction using stoichiometry, delta H's of reaction using Hess's law, bonds. Well, since I have these underlined here, where essentially you can find delta H of the reaction using stoichiometry, you can use Hess's law, you can use the bond breaking, right? Remember the bond breaking, you do the breaking minus the formed, and then you can do the product and the reactant. So we have seen this, this, and this. So we're now going to be looking at enthalpy of reaction from stoichiometry, okay? We are focusing on stoichiometry giving us enthalpy of reaction. Even though we saw a different form earlier where I think, if I remember correctly, you're given one reaction, you're asked to use that reaction to give you the delta H of a different reaction. We're now moving on and looking at stoichiometry and the delta H of the reaction. So we're told in this problem here, a city of 100,000 people used approximately 1.0 times 10 power 11 kilojoules of energy per day. A lot of energy, right? So we have the energy per day. The city's energy comes from the combustion of liquid octane. So we're looking at a, so only these words are the only information you have for this question or this problem. Remember that in figuring out the enthalpy of the reaction, if you're going to be using the stoichiometry route, this equation, because stoichiometry begins with, they just told us somehow that there's a combustion reaction with liquid octane. That means you have to make your own or write your own balanced equation with liquid octane. C8H18 in a liquid state, this is a L, It's a bad looking L, but it's an L, plus oxygen gas to give you carbon dioxide gas plus water gas. So you need to write your own equation out and you need to balance your equation. And it says, of course, combustion of liquid octane to form gaseous water, check, and gaseous carbon dioxide. It kind of gave you a little bit of a clue. Okay. Use standard enthalpies of formation to calculate delta H of the reaction for the combustion of octane and determine how many kilograms of octane are necessary to provide this amount of energy. So we're told, use standard enthalpy of formation to calculate the H of the reaction and determine how many kilograms of octane are necessary to provide this amount of energy. Oh, okay. So here's the thing. We're being told here that this energy that's provided, this energy is the energy that's used by the people in the city, right? So what we need to understand here is each chemical reaction has its own enthalpy of formation or enthalpy of reaction. So I see right here that this equation is balanced. I'm not going to lie. I'm going to just go ahead and use this equation right here. We don't know what amount of energy is released when this chemical equation takes place. So let me write this equation over again. Let me see. It's 2. So I'll try to balance it by just starting with a 2. Oops. Let's start here. We need to know how much energy is released each time that reaction cycle goes through. And then once we know how much energy is released, we can then use the amount of energy required to figure out how much octane has to be burned, right? So let me go ahead and erase this so I can actually start from the beginning because I see right here I'm being a little sloppy. Okay. So let's see what's given in the equation. We're given 1.0 times 10 power 11 kilojoules. And what is this? We're told this is the amount of energy consumed. So this is energy consumed, right? This is the energy that the people need. We have our equation here. Our equation is not balanced. So what I'm going to do here is I'm going to write my equation below here and I'm going to balance it. I know to balance it, I need twice of this because it ends up being an odd number. That's okay. I'm going to write this here plus oxygen. I need to find out how much energy. Actually, now that I'm looking at this, I'm going to take this back. Since I'm dealing with energy of formation, I'm going to try to make, they did say right here, right? Use standard enthalpy of formation to calculate delta H reaction of the combustion of octane. Since I'm going to be using enthalpy of formation, I am going to be making 1 mole of octane. So I want to go ahead and do this by myself. I mean, not copy what I wrote before. And this would change this right here. Let me change this right here. And then CO2, because they did tell you the method you should use, enthalpy of formation. When we usually use enthalpy of formation like that, we end up making 1 mole. So I'm trying to figure out each time 1 mole of this octane is burned, how much energy is released, right? So this is our equation. Let me go ahead and balance it. Carbon is 8, hydrogen is 18. I'm still trying to figure out the question as I'm writing this down. Oxygen is 2. This is our left side. Right side, we have carbon here is 1. Oxygen is 2. Hydrogen is 2. Oxygen is 1. Okay, so my goal right now is to write my balanced equation, and I'll finish reading the equation and the question. Okay, since I'm not going to be doubling this, let's see. I have my itemized list. We'll balance oxygen last. I can start by balancing carbon. Why not? Let me put 8 here and see if that works. Put 8 times 8 will give us what? 16. And then for hydrogen, so for right now my carbons are balanced, right? For hydrogen, my goal is to balance this. So I'll put what? Times 9, right? To make 18 times 9 to make 9. Okay. Now the carbons are balanced, the hydrogens are balanced, but I got 2 oxygens. So these add up to what? 25 oxygen total. But here I have 2 oxygens. So if I multiply this by 25 over 2, I get 25. So I'm going to put 25 over 2. And here I'm going to put 1. Actually, the 1 is implied. We don't put 1 in balanced equation, but you know what I mean. That's 1. Here, my multiplier, aka coefficient, is going to be 8. And then here it's going to be 9. So that should be good. I balanced my equation. They said use enthalpy of formation. That means I'm going to stick with 1 mole of this. Okay. I'm going to erase these because these have served their purposes. So my goal here is to figure out, well, before I decide what my goal is, let me make sure I'm done with the question. What I did was I got to this part right here. It said, use standard enthalpy of formation to calculate the H of the reaction for the combustion of octane. Oh, so we're doing 2 things. Our number 1 goal will be to calculate delta H of the reaction, right? For C8H18 liquid, right? That's our first goal. Use standard enthalpies of formation to calculate the H of the reaction for the combustion of octane. Goal number 1. Then goal number 2 says determine how many kilograms of octane are necessary to produce this amount of energy. Oh, this is a given energy. And so what is wanted from the given energy, which is goal number 2, is kilograms of octane, C8H18. Okay, we can do this. Let me go ahead. I'm going to erase all of this right here. I'm going to erase all of this because I'm starting from scratch. Okay, do we have these numbers? Delta H of reaction, like we saw before, will be, of course, sum of products minus sum of reactants, just like we did before. Sum of products. This is 8 carbon dioxide plus 9 waters. Do I have these somewhere nearby? I'm trying not to go back to the table. Do I have this? I know what oxygen is. Did we do a combustion reaction recently? Okay, so water is, where's my notebook? I don't have my notebook here. I'm trying to use the easy way out, right? So water is, because these numbers don't change. Water is negative 241.8 kilojoules per mole. Okay. So do we have carbon dioxide? Yeah, we had it somewhere here. I told you guys we had it somewhere here. But I have to find octane, right? Water is that. You know what? Let me go back to the table because I'm sitting here trying to read through this stuff here. Okay, this table will be more useful. Water right here, I need, it's water in the gas state, right? So I got the negative 241. I got this right here, 0.8. Then I need what else? CO2, CO2, CO2. CO2 is right here. CO2 is negative 393.5 kilojoules per mole. CO2 is gas, right? They said gas to help us figure out the right one. Now I know oxygen is going to be 0, right? Oxygen, I saw that somewhere here. That's 0. But I need octane. Octane is C8H18. C8, is this somewhere here? I don't see octane. Okay. I don't see octane here. But they may have given to us in the table. Okay. Don't panic in the homework and if you have a question like this in the exam, you will be given all the numbers you need. I'm just going back to the table because the table is accessible to me. Okay, let me scroll back down to where I was and see, where was I? Yeah, they usually give you all the numbers you need to figure out this. Okay, let's see. Oh, so I see here somehow I did have this number for octane. C8H18 is negative 250.1. Yeah, I'm not using this method here that I have written here, so I'm just going to erase this. I just needed a number for my purposes, okay? Because I'm using a different method. The way I worked it out before, I figured it out for double the amount. Now I'm just doing this number here. So I do have the amount for the 8 carbons, so 8 moles of carbon dioxide, and each carbon dioxide is negative 393.5 kilojoules per mole. So I have these written down. Okay, this is for 8 carbon dioxide. And then for 9 waters, I have 9 moles times, let's see, negative 241.8 kilojoules per mole. Right? So this and this cancels out. Now I got to do my math. What is my math? Let's see. 8 times negative 393.5. Negative 3148 kilojoules plus 9 times negative 241.8. Negative 2176.2 kilojoules. Okay, so we take this as negative 3148 kilojoules, not plus, minus 2176.2 kilojoules. So we subtract those, 2176.2 kilojoules, and we end up with negative 4352.4 kilojoules. Okay, so this is the product side. Now for my reactant side, what do I have on my reactant side? For my reactant side, I just have, well, this is balanced. I just have 1 mole of, so I'll say some of the reactant. Because the formula, remember, for the reactant side is C8H18 plus 5 oxygen. Is it 5 or 25? 25 over 2 oxygen, like that, right? Remember, the oxygen is 0, so essentially all we have here is 1 times, or should write it properly, 1 mole times, what's the number I have here? Negative 250.1 kilojoules per mole, like that. Okay, long story short, we have this, negative 250 kilojoules. Okay, let me erase all of this. Erase, erase, erase. Wow. Am I erasing this at all? Okay, let me add a new page because for some reason I feel like I'm not erasing this. Okay. Equal negative 250 kilojoules. Okay. Now we have our product. So delta H of the reaction then, as we know it, at standard state is going to be equal to sum of products minus sum of reactants. And our product right there is negative 4352.4 kilojoules minus our reactant, which is going to be negative 250 kilojoules. Let's see what we get. Oh, so negative and negative becomes positive, so this is plus 250, right? So we end up with negative 4102.4 kilojoules, okay? So we did all this to say when 1 mole of C8H18 reacts with 25 over 2, that would be what? 12.5 moles of oxygen to produce carbon dioxide. Oops, I'm writing this incorrectly. And water. And let me see, the coefficient for that was it 8 and 9? 8 and 9. moles of the products. The amount of energy released here, the delta H of this reaction, is equal to negative 4102.4 kilojoules. Okay, that's what we're saying based on what we got. So I hope we're in the right neighborhood. Let me delete this because this is now useless to me. Okay, before I continue, let me make sure that what we got is similar to what they got, because once we work this out, we're now going to be doing stoichiometry. That's where I got the number from. Okay. See, my number is I didn't want to continue until I made sure that the answers were correct. My number is slightly different from theirs. I'm trying to make sure I did 8 and then 9. Why is my number slightly different? Okay, let me double check my numbers because I see that my number is slightly different from theirs. I hope I multiplied this correctly. I think they had negative 241. Is your answer slightly different from mine? Because I have 393.5. Okay, for some reason my answers are slightly different. Let me double check this math right here. So I have 8 times 393.5. That's, yeah, negative 3148. And then I have 9 times 241.8. Yeah, so these look correct. And so when I subtract those two, negative 3148 minus 2176.2. Oh, how did I get that? Okay, I just transcribed this wrong. It's supposed to be negative 5324.2. Okay, kilojoules. I just wrote it wrong. And then we end up, this is correct, and then this is supposed to be 5. So that's the only part that's off right there. 5, and this is supposed to be 5 then. So let me make sure, and this is plus 250. Plus 250. Okay. So 5074. Let me make sure that's what they get before I continue, because, okay, so 5074 is what I finally get here. So let me write this correctly. Negative 5324.2, and then this ends up being plus 250 kilojoules, and so we end up with negative 5074 kilojoules. Okay, finally I'm set up. So I'm saying, yeah, I had to double check, because sometimes when I'm going back and forth, scrolling back and forth, I just start messing up the numbers. And plus, I was working really late, and should I say really early this morning? Yeah, and that usually affects my focus. All right, now that we have this, so they're saying, okay, now geometry, you still get. Now our new wanted is the amount of octane. They don't want it in grams though, they want it in kilograms. So knowing that each time this cycle of reaction runs, this amount of energy is released, you use this information then to find how much of this octane should be used, okay? So now we're going to say, we're starting a stoichiometry. Our given is going to be the number we had way back here, the 1.0 times 10 power 11. So let me here, 1.0 times 10 power 11 kilojoules. Okay, so starting with that, how many kilograms of octane? Imagine the scientists working on this to figure out the amount of octane a city has to use. So here, 1.0 times 10 power 11 kilojoules. Remember, in stoichiometry, you start with your given, right? So I'm starting with my given. That's my given. And then somehow I have to bring this back to the balanced equation. Okay, so when we start with a given, you're going to use your modified balanced equation relationship. Normally, when we're dealing with a balanced equation, we use a mole to mole relationship of the reactants and the products and vice versa. But now we're saying for every one amount or 1 mole of this compound here that reacts, this is the amount of energy released. Okay. And so, oh, they were saying they use this energy. So the one thing that we have to write here in this case is you can leave the energy here as positive because it's the energy being used by the city. But we have to remember, in order for the city to use the energy, this energy has to be released by the chemical reaction. So to make sure our signs are consistent, I'll put a negative here, and that way I can put a negative down here, negative 5074.2. The negative sign is written from the point of view of the chemical reaction, that the chemical reaction has to release this energy for the city to use it. The other easier way of looking at it is your mass has to be positive. There's never a negative mass, okay? So the mass here has to be positive. So we're saying 1 mole of C8H18 releases this amount of energy. So you see how our stoichiometry is already building up? We're going from energy to moles. From moles, now we can use the periodic table conversion to get the mass. That 1 mole of C8H18 has certain grams of C8H18. Okay. What is C8H18 again? I have all these pieces of paper because I moved my notebook because I've been doing so much stuff, y'all. It's like, yeah, teachers have work too. And then they give us all this work in the end of the semester, y'all. Like, when you guys are busy, so are we. Okay, C8, 8 carbons, 8 times 12 plus H is what? 18 times 1. I can work this right here. I don't have to do it on the side. Y'all know. Okay, we're dealing with C8H18. So we had 8 carbons plus 18 hydrogens. So the carbon is this. The hydrogen is this. So I get 114, right? 8 C8H18. 8 times 12 and then 18 times 1. Okay, I got 114 here. Okay, but they said take it to kilograms, so we can't stop here. We have to take it all the way to kilograms. So 1,000 grams down here, 1 kilogram right here. Finally, we're there. Now we can do our maths. So see, the negative and the negative cancel out here. Now we're finally ready. Am I excited? Yeah, I'm ready to get to the answer. So 1 exponent 11 to the right. I'm putting my scientific notation in parentheses, times 114 divided by 5074.2 divided by 1,000. It's a huge number. I get 2246659.6. So let's see, y'all. I'm gonna move decimal. Okay, 1, 2, 3, 4, 5, 6. I know, it's such a shame. Okay. Hey, the city knows how much octane they should use. They need about 2.25 times 10 power 6 kilograms of octane. That's a lot of octane. Let's see if they got this answer. Okay, our molar mass looks similar to theirs. Okay, they got what we got, or similar-ish. And we got what they got. Yes. I'm relieved there. Because this is the last question in this chapter. Yay. Okay. I would say the tricky part about this chapter, or not this chapter, this last part was they normally give you the enthalpy of the reaction. You don't have to figure it out before you use it. But this question is one of those real life application questions, right? Some people are hired by companies as engineers, and they will have to, yeah, they get paid the big bucks, and they have to figure out how much that company is consuming in energy, because when you have a company, you have to know what your cost is. One of the biggest costs is energy, the energy used to power the plant and things like that. So of course, maybe the machine, there probably will be a machine that's figuring all of this out. But if something goes wrong, the engineer has to know the math to be able to do it manually or by calculator to solve this, right? So they hire, even though they may have a machine, they hire a human to overlook the machine, right? To look over the machine to make sure the machine is working right for accountability. Anyway, yeah, that's it for this chapter. I don't want to start 10 today. We'll start 10 next week. Any questions about this chapter? I'm just, yeah. This is one of those chapters where the conceptual part was a little iffy, but the math part was great. So, it took a while to kind of get the concept delta H, where it's going, where it's coming from, but you want to make sure you understand this well. If you're going to 1412, it does help a lot. As I said, I just finished covering a similar part of this chapter in 1412, but we go into a lot more details. But yep, if you don't have any more questions, this is all I have for today. So hopefully I can save this and actually post it. Okay. Okay.